What about now?
Oh, it got bigger.
Okay, is it better this way or you need it smaller?
Looks good. Looks good.
Okay, so yeah. So again, as I said, you probably see typos. This is actually a good thing to have. And unfortunately, my pen, I need to figure it out because even though I pre-prepared the slides, I wanted to make some notes, but it won't be possible. There's an issue with the thing. Hopefully, I can solve it before the next session. Yeah. Okay, so let's see. Can you see this slide, the next one?
Yes.
Okay, so before we start, it actually worked, especially for the newbies, to go through some mathematical jargons that you will come across, okay, during this boot camp, but also obviously as you read books and outside the boot camp. The first notion is that of an axiom. So an axiom is, something, is an assertion, a statement that one accepts without proofs. So it's given as a starting point for deducting or for constructing and deducting other things within a mathematical system, or we could be like within an axiomatic system. Okay, and they normally show up in definitions. Definitions are like precise, like explanations of a meaning of a mathematical concept or term, in order to ensure like clarity. Okay, because mathematicians don't like ambiguity. Theorem, as most of you will know, are statements that have been rigorously proven, generally by humans. I won't touch the thing about computer-aided proofs and these things. It's being a subject of huge debates. But yeah, they are rigorously proven, whether by a computer system or a human. And these, normally in our case, these theorems are very important central results in mathematics. And the other term you will come across is this thing of a corollary. So this is like a consequence, a follow-up from a previously proven theorem. Another thing is lemma or lemma. How do you pronounce this in English, George? You are my linguist.
Lemma.
Lemma. Okay, so yeah. So lemma is some sort of a helper, really, something that you use to prove something subsequently. So these are all things that you will come across. And here, propositions are also theorems, okay? And in our case, we will reserve the word theorem just for important stuff. In fact, today you will see, just to show you, I will stick some propositions in a thing for you to try to tackle. Conjecture is some assertion and a hypothesis based on, evidence or facts that mathematicians think are true, but has not been proven nor disproven. So these are like, jargons that you will come across, as we go along, but also not just within the context of this boot camp. Okay. Now, I'm going to the first. Yeah, go ahead.
A question from Chuba. How do you distinguish between a lemma and a corollary?
Okay, that's very interesting. Can we go back to that in the thing at the end? This is a very interesting point of discussion to follow up with. But generally, they are like mathematicians are very careful. They are actually stated. So the person giving it to you, they will say this is a lemma. So I'm using this to go, and this is a corollary of something else. Yeah. So in your case, if it's you doing it, obviously you have to like, okay, are you starting from it? Do you want to prove the theorem, or you already proven something and that thing? You are using that as a launch pad to prove the other, another truth. Yeah, so that would be your corollary of what you already proved. Sorry. Okay, so here's the first definition. This is the most uncomfortable definition for me because this is why we call it naive. It is so naive that I would rather just skim through it, so we are fine, so we don't get into the rabbit hole of going through and debating. So a set, I will say, a set is a collection of distinct objects called elements of the set. Okay. This is very, very naive, okay? I will claim that rather than us going through this, trying to come up to, even if you disagree with this, it is very naive, especially this condition of distinct. If it's too much, I would argue that as we go along through the course, you will see why it is important for object in a set to be distinct. It makes life easier for you. You will see that by yourself. Okay, so for example, let's suppose using a set builder notation. So set builder notation is these bracelets. You input your elements of the sets. Obviously, we are dealing with the finite set. We will define the notion of finite, but yes, just for the time being, I can mention it. Appeal to your human intuition, which is sometimes can be very dangerous in mathematics. Yeah. So let's X be A, B, C, D. And Y be A, B, C, D, A. So according to our definition, this is a set. This is not. In fact, if you give this to a mathematician, they will just assume you mean this. You are just repeating the A. Okay. The other thing is if X is a set, and let's say alpha is an element of X, we write this thing here. This E. It's red. Alpha belongs to X. Otherwise, we write alpha does not, this thing here, meaning that alpha does not belong to X, to indicate that alpha obviously is not an element of X. So for example, let's take a toy example, concrete example. I think this is the only concrete example you'll have today. Let's suppose X equals 2, 10, 1, 6. Then obviously 6 belongs to X, right? Because it's here. But 11 does not, because we don't see 11 here, right? This also just a quick, again, this is another thing for another topic, the Russell paradox. Now that we are talking about, membership, belonging and these things, one has to be very careful, especially with the set theory. For example, I appeal to your for you to look at this. Suppose that S is a set of all sets which are not elements of themselves. So let's say using the set builder's notation, S equals A such that A does not belong to itself. The question you put is, does S belong to itself? So the popular version of this is like, consider the barber who shaves all people, or all people who don't shave themselves. The question is, who shaves the barber? So I'll put, this is just interesting. I guess everyone can see. Is there anyone who cannot see a contradiction here? Whichever question you ask. So this is the Russell paradox. That's why I'm just mentioning this. This is nothing for you to know. This is just a side thing, just for you to know that one has to be very, very careful about when we talk about memberships. That's why axiomatic set theory exists, in order to try to solve this, which we will not go into. So that's the first definition of a set. The other definition is this notion of empty set, which is denoted like this, is a set with no elements. Again, I will appeal to your human intuition, even though knowing that that can be very, very dangerous in mathematics. So a set without any elements. And using the ZFC, this means ZFC, Zermelo, Frankwell, and plus the axiom of choice. We will actually talk about axiom of choice at the right moment, I think in the next session or the session after, because it will show up on something. I will just briefly mention it. It guarantees existence of the empty set. So the empty sets exist. It can also be proved that the empty set is unique. You don't need to worry about this. Just take it as fact. And in fact, the empty set is very ubiquitous in mathematics, in modern mathematics built on set theory. You will see this, for example, when we are talking about topological spaces, for example, the notion of topology, you will see needs the empty set. So it's everywhere, really. Okay, so let me get off this slide because it's the most uncomfortable one because of the very naive definition of a set. Does everyone agree with me about this, the definition of a set? In a naive way, how would you naively define this? Is there anyone who would define it in a different way? No, okay. Any question, George?
There was a little discussion about the wording, axiom, theorems, corollaries, and so forth. I think that can wait.
Okay. So the next definition I will go through. So we have a lot of definitions. This is the key to get as much as things wrapped up today, so you can go and think about it, and we can move on to topology as soon as possible. But we still have few sessions to go on this, so you can get all the naive set theoretic notions you need. So suppose, and again, the eagle eyes. Okay, I see a typo here. Yeah, I guess it doesn't matter here. This thing, yeah. Let X be a non-empty set. Okay, we say another set, let's call it A, is a subset of X, and we write this notation. If whenever alpha belongs to A, it follows that alpha also belongs to X. In other words, A is a subset of X if everything in A is also in X. Okay. And obviously, this is clear if you cannot see this, obviously by definition, every set is a subset of itself. Now, here's a very interesting question. Let's see, just to, again, as I said, today is a test water. Is it true that the empty set is a subset of X, where X is any set?
Yes.
Okay. Who doesn't agree? You can think about it. We won't, even if you don't agree, it's okay. That's also fine. You can go and think about it. But it is true. In fact, I recommend. I don't know who said yes. Maybe on Discord or on Zulip, you can help whoever is not convinced about this. How come something that we just said before has no elements is actually a subset of anything? Okay. The other thing is, if Y is not a subset of X, we normally write this thing. So we put, it's pity my pen is not working, to indicate that Y is not a subset of X. Okay. And this is a proposition. So let's X, Y, and Z be sets. If the claim is, if X is a subset of Y and Y is a subset of Z, then X is also a subset of Z. So meaning that the inclusion or this thing, the notion of subset is transitive. Okay, and we can use this actually to go through another definition, which is the notion of the equality of sets. Okay, so let's X and Y be sets. We say X equals Y if X is contained in Y and Y is contained in X. In other words, if anything in X is contained in Y and anything in Y is contained in X. So we say the two things are equal. Okay. When the two sets are not equal, we write this, obviously, the thing. Now here's a question, using again set builders and these toy examples. Let's say X equals alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, and alpha 6. Okay. And let's say Y equals alpha 6, alpha 1, alpha 3, alpha 4, alpha 2, and alpha 5. Is X equals to Y?
Yes.
Yes.
Mm-hmm. It is. Is there anyone who thinks otherwise?
It is easy to see in this case. It might be hard to see in a bigger example.
Yeah. Yeah. The reason I put this example is because my experience with newbies, they normally look at this and then the ordering becomes, but we don't mention on the definition and of equality of set. We don't mention anything about order. This is another tip. In mathematics, when the definitions are carefully crafted, so when you are asked to use a definition, when you are using, just do not make any extra assumption, okay? In here, in the definition of equality, we didn't mention anything about ordering, so it doesn't matter if they are the same. You know, we just happen to, you know, shuffle them around, right? If you have, you know, a set, I don't know, of 6 chickens, okay, that's a bad example, because, you know, they might have different, yeah. But yeah. Okay. The other definition here is if A is a subset of X, then we say A is a proper subset if it's different than X. There's actually a way of writing it, so we would remove this this line here, so it will just be this thing to indicate that it's a proper subset. Okay, so that's the notion of subset. So you know what a set is, you know what a subset is. Okay, this is something that you need for topology. Okay, so let's move on to the next thing that you need as we move for topology. The intersections. Let's see, actually, yeah, intersections. Okay, so let X and Y be sets. The intersection of X with Y is defined like this. So, you know, all the alphas that are simultaneously that are both in X and Y. So this is as the intuition, you know, where they meet. This is basically their intersection. So we have X here, and this will be the intersection where the two cross. And here's a proposition. This will be part of the assignments that given any sets X, Y, Z, the following properties hold. Okay, like the intersection of the set with the thing is with the empty set is empty. Okay, and this thing here as well, commutativity, and so on, associativity of sets as well. And finally, in terms of intersection, this gives us opportunity to define the other notion, which is, I don't know if you can see this. Can everyone see definition 1.6?
Yes.
Yeah. So X and Y are said to be disjoint. Yeah. So if their intersection is empty, so if this here is empty. Okay. So there you go. Another thing that you need to know. So the other thing is union. Okay, this one is a little bit tricky. So let X and Y be sets. The union of X with Y, you know, the union, so you are bringing the two together, is all the alphas that are in X or formally or in Y. But this or in mathematics, this is not exclusive. So the union can actually also contain their intersection as well. So it might contain elements that are in both sets, okay? So very, very careful with this. And then here's a proposition as well, similar to the intersection here. You also have these nice properties here, like the commutativity and the associativity. I hope this is where there's a danger, because there will be a lot of other lines. There might be a typo or something. But if you see it, please do let me know so I can fix the slides. So this, again, this will be homework. This will be like kinder, very, very easy. As I said, you know, we are starting very, very easy today. And now we'll go through the notion of complement. There will be like 2 notions. I hope I didn't make any typo here. But the one that most pertinent to us is this one here. But nevertheless, let's go through the most abstract one, which is this one called relative complement. So given 2 sets, X and Y, the relative complement of Y in X is defined as X minus Y. So the alphas that are in X but are not in Y. Okay. And the other notation for this for the difference is also this quotient here that people normally use to denote it. And this one here, let's A be a subset of X. So the absolute, this is normally in a lot of textbook when they talk about complement, they actually mean this one, where the complement of a subset A of X in X is all the sets, sorry, all the alphas in X that are not in A. So suppose X is the entire thing here, okay? And suppose inside this thing here, this is A. So everything outside that's not in A, this is the complement. And now, homework exercise. This is really very important. That's why I didn't give any examples, because this is abstract mathematics bootcamp. So, the less examples, the for me, the better. So you can, start using, start getting familiar with abstraction, to start doing things without actually, thinking about examples. Just look at the definitions and try to work with the forest as opposed to the individual trees. So yeah. So here's exercise 1. This will keep you busy, especially the newbies. Let X, Y, and Z be sets. The question is, which of the identities below are true? Okay. Obviously, you need to look at the definitions that we gave of, unions and the intersections and so on for you to be able to do this. And then the exercise 1.1 is these guys here, this identity. This is the hardest, but yeah, this is also doable.
4 and 5 look similar.
Yeah, sorry?
4 and 5 look identical. Oh no. Okay. Never mind.
I made a typo. Yeah.
Different. Yeah.
Yeah. So yeah. So I really do encourage, as you can see, I mean, if you want to like, construct like concrete sets, finite set, and try to look at this, you can also do that. But I recommend you to do it in abstract without actually constructing any concrete example. Just you can also use a Venn diagram as well if it helps you. But this is the whole thing to try to get your mindset, used to when you see a mathematical definition, the first thing that comes to you is not, can I see an example? No. Instead, it should be like, what can I prove with this? What statements? What things can I build with this? So this is why I'm deliberately not giving any example. This also helps with my laziness as well, so I don't have to produce much, right? So yeah. So then we have. I hope I'm labeling the exercises correctly, and then you have this involving the complements as well. Which of the identities below are true? So obviously you need to find out which ones. Not all of them are true. At least one will be true, but the question is, are there more? So you need to figure it out. So I really do encourage. So that's it for today. As I said, it was going to be a very easy session, just to warm the waters, to test the waters, to see how everyone is in respect. Especially, I would like to see assignment, because this was a very, very easy session. It would be nice for you guys to to go through the problem sets it mentions, these exercises. So these will be the ones that I will assign, and the propositions as well, for you to try to keep yourself busy. So that's it. Let me go back to, for the advanced ones, like for the advanced attendees, I'm so sorry. Today it is. I just wanted to start with something very, very basic, just to test the waters to see. Yeah, so the slides will be uploaded on GitHub, and then I will also link them with the assignment. So when you see the assignment pop up, I will reference to the slide to put the URL on it. Yeah, I see a comment here, very interesting. Russell's paradox was the reason for axiomatic set theory. Yeah. Okay, so maybe I'll stop recording so people can feel free to tell. I would like to see, was it easy? Was it hard? The session, so I can get a feedback, so everyone, no one, probably most of you have seen this. So people on YouTube, I'll see you next time. Let me find the stop so everyone can be at ease. Where do I stop recording? Hang on a second.